Welcome back, STEAM cadets. Professor L here, and let's jump right into our explainer for Mission 002. Today, we're tackling a massive, real-world engineering problem for platinum stars mining. We're moving past just looking at the outside of the headgear, and we're diving deep into the actual machinery that does the heavy lifting. So grab your engineering hard hats, because we've got 6 crucial PAT investigation marks on the line today. All right, here's your mission briefing. Platinum Stars needs to transport miners, equipment, and a staggering 10 tons of platinum ore up and down a 500-meter deep mine shaft. Now, sure, you could just hook up a gigantic, super energy-hungry electric motor to pull that massive weight up, but powerful motors use a ton of electricity, and they're incredibly expensive to run. So, today's mission asks a critical question. How do we efficiently and safely transport these heavy loads 500 meters underground without completely burning out our winch motor? Before we crack open the PAT questions, we need to establish a core engineering principle, and it's the very thing that's going to save our motor. It's called a counterweight. A counterweight is exactly what it sounds like. It's a weight used to provide an opposing force that helps balance a mechanical system. Think about a seesaw on a playground, right? If a heavy adult sits on one side, it just slams to the ground, totally unbalanced. But if another adult of a similar weight sits on the other side, the whole thing balances out. Suddenly, it takes barely any effort at all to move them up and down. Well, a mechanical counterweight does the exact same thing. It gives us an opposing force to balance out a massive load. And that brings us perfectly to what we're analyzing today. We've got 2 different mine hoist setups straight from your pad. System A is over on the left, and System B is on the right. We have to analyze these 2 mechanical systems to secure our 6 marks. You really want to look closely at how they're built, where the cables go, and what specific components are doing the lifting. To answer our investigation questions correctly, we can't just glance at these. We have to really read the engineering story they're telling us. Okay, here's question 1 from your investigation, and it's worth 1 mark. What are the differences between the 2 mine winches shown here? Pause mission. I want you to actively compare the 2 systems. What components can you actually see? What's changed between the design on the left and the design on the right? Take a second and write down the major mechanical differences between these 2 winches right now before we move on. All right, we're back. The engineering secret here is exactly what the examiner's memo is looking for. Notice how System B uses 2 sheave wheels, and they're working off the very same winch drum. One sheave wheel is used for the cable that lowers the mine cage and the skip. But that second sheave wheel, that is specifically there for the cable that lifts the counterweight. System A, on the other hand, only has a single sheave wheel and absolutely no counterweight at all. Make sure you lock that 1 mark in. Let's keep the momentum going with question 2, also worth 1 mark. What do you think a counterweight does for a mine winding system? The PST is actually giving you a brilliant hint here. Pause mission. I want you to close your eyes and imagine you're physically winding that massive winch drum entirely by hand. What exactly is that counterweight doing for the whole mechanical system as you try to lift a 10-ton skip? Write down your thoughts. Let's see how your thinking lines up with the official memo. The crucial takeaway here is that the counterweight produces a rotational force on the winch that pulls in the exact opposite direction to the heavy weight of the cage. Because these 2 forces are literally pulling against each other, they partially cancel out. And the result? The winch motor requires significantly less rotational force to move that massive cage, which saves energy and drastically reduces the everyday strain on the equipment. You guys are displaying some excellent engineering thinking so far. Let's tackle question 3. Which bumps us up to 2 marks. Which of the 2 systems in the picture do you think will need the largest motor? Explain. Pause mission. Take a look at System A and System B. Tell me which one needs the most powerful motor. And listen, here's a pro-exam strategy for you. Never stop after just naming the system. You absolutely must explain why to get that critical 2nd mark. Go ahead and write down your answer now. Let's see how this all builds on what we just learned. For your 1st mark, you need to identify that System A needs the stronger, larger motor. But why? Well, for your 2nd mark, the memo states it's because System A does not have a counterweight to reduce the load on the motor. That poor motor in System A is forced to do 100% of the heavy lifting all by itself. By simply adding the counterweight in System B, we can actually get away with using a much smaller, way more efficient electric motor. We've talked a lot about efficiency, but now it's time for question 4, worth our final 2 marks. Which system will be safer? Explain your answer.
Pause. Mission. Engineering is never just about saving electricity, right? It is fundamentally about protecting human lives. Imagine a catastrophic emergency where the winch motor suddenly fails completely. Which system would you rather be riding in? And why? Get your answer down.
Let's check the memo. System B is definitely the safer option. And here's the explanation for your second mark. If the motor fails on System A, that heavy 10-ton cage is going to plummet. But with the counterweight in System B, the two weights on either side of the sheave wheels are more or less perfectly balanced. Because it's balanced, an emergency cable brake can easily grip and stop the fall. Always remember, balance plus braking equals a vastly safer system.
Okay, Mission Control, here is your rapid-fire debrief. Lock these 4 key takeaways into your memory banks so you can completely ace this PAT investigation. 1. The counterweight system uses 2 sheave wheels working off a single drum. 2. The counterweight provides an opposing force that creates balance. 3. Because of that reduced load, a smaller, more efficient electric motor is needed. And 4. The balance system offers much greater safety because emergency brakes can actually stop a balanced load.
Junior engineers, you've absolutely crushed it today, but I have a final independent test of retention for you. When this explainer finishes, I want you to close your books, hide your notes, and go find a friend or a family member. See if you can explain to them exactly how opposing forces allow engineers to use a smaller electric motor on a massive mining winch. Trust me, if you can confidently teach this concept to someone else, you have truly mastered it.
Next time, in Mission 003, we transition from investigating the problem to actually designing the 10-mark headgear solution ourselves. We're going to write professional briefs, identify specifications, and navigate real-world constraints. But I'm going to leave you with this provocative thought. Knowing how to lift a 10-ton cage is one thing, but do you have the engineering creativity to design the structure that keeps the whole thing from collapsing in on itself? Keep thinking like engineers, and I'll see you on the next mission.